And then we have a squared error function that I call f, which is quite complex. But in the end, it's something like a second-order equation. And we want to minimize this equation, so we compute the derivative of this resulting equation, set it to 0, and then we have a linear system here. Okay, so, and here are the terms that we must linearize. Both terms are computed using this Jacobian, okay, the Jacobian of the error. And an important point is that a Jacobian is the matrix of partial derivatives of the error in every dimension of the state. But one of the main advantages of computing this is that the Jacobian is sparse, because the error between two nodes depends only in the position of those nodes. Does not depend on the rest of the system. So in the rest of the system, everything is 0 except in the positions associated to the two nodes connecting an edge. Okay, so Jacobian is mostly sparse. Is 0 in almost all places. And so these two variables, b and h, are also sparse. And then solving a linear system based on a sparse matrix is something that can be done quite efficiently. Then we can use techniques for solving this linear system, there are many techniques like Chauvet's decomposition and others. Okay. So, and this is basically what is done in the optimization step. There are many other techniques for optimizing a graph, but this is the most popular. How to build a map is the role of the front end. So, while the back end focus on this mathematical task of optimizing graphs, how to build a map is quite different. We need to solve the place recognition problem. We need to determine when the robot is seeing something that was already observed. And there are lots of techniques here. There are many works that propose novel techniques for place recognition. But depending on the sensor, we have, for instance, if we use a rangefinder like laser or sonars, we usually do scan matching. But today, what is most popular are the use of cameras, and in this case, the most popular techniques are based on feature matching. Let me see. As I saw here, we reached 45 minutes. I don't know if you want to make an interval.
Yeah, let's take a break.
And then I'll continue later. Okay.
Okay, thank you. So, welcome back, Professor. I will let Professor Renan continue with the presentation.
Okay, thank you. As I was talking, an important part of SLAN is the front end, right? Is how to build a map. And the idea is to solve place recognition. What is place recognition? Determine if the robot is at the same place in different occasions by comparing the observations made in those different occasions. So there are lots of place recognition strategies. for instance, align points to line segments, because in SLAM, the approach incrementally builds a map, and then we can compare the local observation, the observations of the objects surrounding the robot with the objects in the map, in this map that is being built. We can perform matching of points, we can perform matching of scans, and we can compare features extracted from images, for instance. And this is what is the most popular approach nowadays, to extract features from images, compare depending on the descriptors used, like SIFT, SURF, or which is the most popular feature-based one. But the main problem is how to handle highly ambiguous environments, because there are lots of objects in the environment that appears in different locations, and there are many scenarios that everything looks the same, and in those cases the only solution is to analyze long information sequences. And I will show an example of a SLAM analyzing long sequences of images, but here are examples of maps that are built based on scan matching. So we have a laser. The laser makes a range of readings. Lasers are used both in ground robots or in vehicles. For instance, here is the Stanley vehicle from Stanford that won the DARPA challenge, and basically what the car, one of the structures of the car was make a map of the surroundings of the robot using multiple lasers. With feature matching, the idea is to extract features from images captured from cameras in the robot and try to match those images and detect matches, detect loop closures, for instance. One of the important things that are being studied today is how to adapt to changes in environment, appearance, how to detect dynamic objects or semi-static objects. Semi-static objects are objects like furniture or even doors that can be open and closed, windows, something, or trees that grow, and something like that. Objects that can change, but over long periods of time. Okay, and this is problematic, and this is something that is highly studied. So here's an example of the OrbSLAM, which is a popular technique, one of the state-of-the-art techniques in SLAM that performs feature matching to build a map. And it's called OrbSLAM because it uses the feature descriptor orb. And here's an example of a vehicle moving in the street. It's detecting features. These green squares are features. And at the bottom is the map, the graph built with these observations. Each one of these blue marks are nodes in the graph. Okay. And the robot is moving, the vehicle is moving, capturing information, and what the approach is doing is performing the matching features to detect this relative motion between two frames, and also to detect possible loop closures. In this case, it didn't happen yet, loop closure, but then later it will happen. So the vehicle is moving, then it will return to a region that it was already observed, and then it will start to generate those constraints made on observations until at some time it will perform a loop closure. When it performs a loop closure, the graph is corrected through the optimization process, and then the vehicle continues moving. At the end, yes. The robot keeps moving. Here detected another loop. Here's the complete map, the final reconstruction of the map, and the ground truth is here. Here's the map built using this method of SLAM. Okay. Another example is SLAM applied in environments with changes in the appearance. I have one of the most popular, no, it's not that one. One of the most popular approaches is proposed by Milford in Australia, is the SEXLAM. And in this situation, when we have such drastic differences in the images, perform a feature-based approach, detecting features on the left image and on the right, it will not work properly. So here, the idea is to analyze long sequences of images, trying to reduce the noise in the image. And so what SEXLAM does is work with low-resolution images and use some other type of feature that only extract let's say major features on the image. For instance, there is a road and there is a sky, something like that, and perform this matching that is not too precise, but check long sequences of matches. So if you are able to match, let's say 20 frames in a row, even though those matches are not quite strong as the matches of OrbSLAM, but then you can say that you are in the same region. Okay, and this is something that one of the problems that are studied today. Okay. So, regarding SLAM, this is what I plan to talk. Now I'll talk about another problem, which is the integrated exploration, or active SLAM. In integrated exploration, we need to perform localization and mapping, that is SLAM, and also planning. Most of the techniques usually consider SLAM as a black box and focus on planning. What are the common guidelines? Avoid featureless areas. Because, for instance, if you are working with cameras, you want to observe images that have lots of features. If you are performing your SLAM and you are looking, for instance, to a wall, probably the slam will fail. Okay, you need to have some kind of good strategy for motion. In the examples that I've shown, with the vehicle moving in the streets, always there are lots of features, but depending on the problem, sometimes you do not have. And another common guideline of active SLAM or integrated exploration is to try to revisit areas that have high uncertainty. Okay, because by revisiting you can observe new things and possibly match more observations, and by doing this you can decrease the uncertainty. When you decrease the uncertainty in the localization of the robot, you improve the map. And another point is that when you perform exploration, when you are building a map, usually you want to build the map as fast as possible, move the robot in the regions that you do not know. That means you try to maximize the information gain. But in an integrated exploration, you also want to balance this information gain with the return to known areas. So how to define this balance is an open issue. And another common guideline is to try to close loops as much as possible. Okay. Well, here's the example of the importance of closing loops. And as the robot moves, the uncertainty grows, and you can only reduce uncertainty when you return to known visited areas. Okay, so closing loops is important using EKF SLAM, is important using graph SLAM, is important using any method of SLAM. Okay. Some of common approaches for active SLAM or integrated exploration. There are greedy approaches that are based on going to the closest frontier of visited and unexplored space. There are approaches using potential fields that move the robot always to the closest frontier also, but not only the closest, but sometimes the most wide space to avoid collisions. This is a characteristic of potential fields. There are approaches that are loop-driven. They try to close as much loops as possible. And there are some approaches based on simulation, based on trying to estimate the information gain that the robot will get going to a particular region. So you simulate the motion and try to simulate what will be the gain. Simulation-based approaches are usually very costly. Okay, so loop-driven approaches are probably the most popular approaches of integrated exploration. A traditional approach is detecting opportunities to close loops. These are approaches being applied over graph-based SLAM. And the idea here is to check the distance of, when you insert a node, you check the distance of two nodes. The distance, the Euclidean distance between the position of the nodes and the distance traversed in a path over the graph. So when the difference becomes larger than a given threshold, you say well, perhaps I'm close to reaching an already visited area. So this is what we've done, what this method does to detect opportunities to close loops, and when it detects, it set the known position as the goal and guides the robot to close this loop. Okay, so the idea is to generate positions of interest that tries to close the loops. But I'll show you a technique that our group proposed. Our group here in Porto Alegre, but integrated exploration, I can say that is the most the problem that we study, that we most study, that the works of Edson Prestes, even mine and other colleagues were focusing on integrated exploration. Here is an example of closing loops, trying to return to regions that the robot already knows, using potential fields that are one of the techniques that Edson proposed. And I told about potential fields yesterday, but potential fields are very good to generate safe paths in the environment to avoid collisions. And it is something that Edson made in its PhD, which is Edson proposed this exploration using boundary value problem. The boundary value problem generates a potential field, so it uses a Laplace equation applied in the environment, such like basically we set boundary conditions, where the boundary conditions are unexplored regions are attractive, obstacles are repulsive, and then we compute a potential field given these boundary conditions are Dirichlet boundary conditions, and then we solve a second order differential equation and using a numerical method, which is Gauss-Seidel, and then we compute the potential field in the environment. So at the right we have a potential field in the environment where black is the highest potential, white is the lowest potential, and the robot in red is guided to the direction of the lowest potential. So we follow the gradient descent that goes in the middle of the corridor, stays far away from obstacles, and explores the environment. It works. It's something that this boundary value problem generates an emergent exploratory behavior, generates smooth trajectories far from obstacles, but it's not that good when to perform, for instance, loop closure or revisiting regions that we already know, and it's something that is costly in large maps. Okay, but it is a very elegant method. It works quite well, but only in moderate size environments. Our approach was to perform loop closure using potential fields, and the idea was that we call it Ouroboros, was to generate these attractive potentials behind in regions where the robot already visited, but behind the robot, and close the propagation of the potential using shields behind the robot. So with this, the only possible way for the robot to return to that already visited region is closing loops. Okay, it's a quite simple strategy, but it works very well. And as the robot moves, the shield follows behind the robot, and when the robot reaches a goal, then we let the robot explore and generate new loops. So there are some optimizations. We used a Voronoi diagram to improve the computation of the potential field. Instead of computing a potential field in every cell of an occupancy grid, we compute the potential only in the Voronoi. So it becomes much faster than the traditional potential field approach. So this is the concept. Here I'm presenting the gradient descent in every cell, and here's the robot following this gradient descent until it reaches the original position. Okay. There are some aspects that we must consider while building this shield. We only generate goals in regions that are already visited, because otherwise, if we do not take care of this aspect, sometimes we can generate goals in unreachable regions, and then the exploration will fail, right? So here's the example of the potential field computed in all cells of the environment, and the potential field computed in a local window using the Voronoi diagram. Voronoi is basically the medial axis of the free space here. Well, here's an example of the local window that we use. Since computing a potential field is something that is efficient in a limited space, for instance, in a local window, we only use a local window, while traditional potential fields compute in the whole map, and this, after some time, becomes quite costly. In our case, this is not a problem. Here's the algorithm, but I will not enter in details. But basically, at each time we update the goal, because the map can change using Slam. We update the goal, then we update the shield, propagate the potential, and move the robot. It's basically this what is done in our algorithm. And I'll show some results, but this is the robot that we use. It's a Pioneer 3DX. It's for indoor environments. We only use it laser here, and we test in different environments. We test it here in our building. And the idea of the map is to close loops as much as possible. So I will just show the results. Here, in black is the local window, right? This is the local window, and this is the null region. In green is the bounding box of the space that we already know. And then the robot moves, closes loops. It closes this first loop, and then it keeps going and closing loops surrounding these objects. Keeps going. And it is a method based on potential field. Here in the local window, we compute this potential field. And in practice, closing loops generate good maps, and we compare these. Our approach with an approach based on frontier guided exploration, such as the traditional potential field. And these are some examples that our approach by closing many loops here at the bottom is the loop closure approach that performs this many this circular behavior, while the potential field does not, and the map generated by potential field can be very, very wrong. Here's another example. Another thing is that potential fields, traditional potential fields, sometimes suffer with a flattening problem, where all the potentials become too similar and the robot cannot detect where to go. When we use a local window, we do not suffer this problem. Okay. Here are our results, just showing that our approach is much faster, because potential field must compute in every cell, and our approach does not. And here's an example in our building, and using the loop closure approach, we obtain better maps. Okay. So this is one approach of potential fields. Integrated exploration, and just to conclude, integrated exploration is something that it is still an open problem. There are very few works in this field of study, and it is very hard to determine what are good approaches, what are bad approaches, and it is quite an important task. Islam, on the other hand, is vastly studied. There are many people studying, but also there are lots of open issues, because when the community solves an aspect of the problem, the guys generate a more difficult problem, for instance, performing Islam at different seasons of the year, or something like that, or in larger and larger environments. Okay. So this is what I was planning to talk to you. Let me go back here. Any questions?
You have some on the slider.
Okay.
Should I see the microphone?
Yes, we have a microphone.
In that case, I can just ask them.
Yeah, sorry. Well, we have a question here. It's a bit loud. So.
Yeah. I wondered about when you compare features in images, how do you avoid the search space getting bigger and bigger when you try to do loop closure detection?
Yes. Yeah. This is many of the techniques compare the current image with all past images, and this is it's problematic. So there is a limit on the size of the maps that we can test, but there are others that only search in a given window. So we only check when you already have an estimate where the robot is, you can eliminate many of the possible images. So if you are working with a graph-based approach, you have the uncertainty associated to each node, and then this uncertainty grows over time. But you can only make the comparisons with nodes that the uncertainty intersects the current node, so you can restrict a lot. But there are many methods that are not worried with this. Saxlan is one of them. because it checks sequences of images, and it uses it does not use features, but it uses some more simple approach. Is more faster it's faster to compare. But usually the main idea is to restrict the search for loop closure. You have some idea where to look. Okay.
Any more questions?
I have one more. Has there been any studies on active SLAM using multiple agents or multiple robots?
I don't know. I don't think so. There are very few. There are some works of exploration with multiple robots, but there are a few. But I do not say that it is exactly active SLAM. They usually just try to build a map as fast as possible. So it is a frontier guided approach. They are not that worried with closing loops and this another common guidelines that are presented. But so active SLAM, there are, I think, very few, and most of the techniques in active SLAM are with a single robot. All those techniques that are presented are with single robots. Okay, with multiple robots there are some of exploration, but just simple exploration.
Any more questions? Okay, I do have a question.
Okay.
I'm not very familiar with the topic, but you mentioned that you can use a graph-based approach. So you
Sure.
have a big graph, and then you can perform some optimization on it. So I'm wondering if it would be possible to decompose that big graph into subgraphs and then solve independent optimization problems and then combine them to make the optimization more efficient.
Yes. There are some hierarchical approaches for optimization, and in fact, this is a quite popular approach also to decompose the graph into subgraphs and optimize only the parts that change it. But it's not the most popular technique. The most popular technique is to optimize the full graph. This optimization technique is there is a framework called G2O that has some state-of-the-art optimization, and but it considered the full graph. But the same authors that proposed this framework presented some works with hierarchical approaches that decompose the graph. So that it is something that has been studied.
Okay, and a related question is that you could use the knowledge of previous robots and incorporate this knowledge into new ones. So maybe they have already solved some similar problems, so they do not need to start from scratch.
Yes. SEXLAN, for instance, is a technique that compares different trajectories captured at different times, perhaps even by different robots, different vehicles. And the problem is just to find the place recognition, to solve place recognition between the observations. So it does not depend, you doesn't need to always start from scratch. In active SLAM, yes, the idea is to build a map. So all techniques that I know in active SLAM start from scratch, but in SLAM, this is not a requirement.
Those are old questions. If you scroll to the bottom. There you go. Those are the last ones. Relevance.
So here we have a question, how is the uncertainty in areas measured?
The uncertainty where?
How is the
Can you repeat?
How is the uncertainty in areas measured?
Okay, how the uncertainty is measured? It depends. It depends on the. It depends on the type of the sensors, the types of the technique that is used. There are many techniques, for instance, for scan matching. They're already the result of the matching gives us a mean and a variance of mean and a covariance matrix. Using feature-based strategies, I do not know quite well how they perform how they estimate the uncertainty. The uncertainty in the motion is easy to do. You have a noise in the motion, so we just use this noise, apply it depends on the velocity of the rocket and something like that. But the uncertainty of observation, in some ways, many approaches consider a fixed uncertainty, because you cannot guarantee that the match is correct, but it depends on the strategy. That does not know quite well how it is used, how it is defined, the uncertainty. I know using laser and using ground robots is what I worked here. With cameras, I do not know quite well how they do. I would need to ask to the guys that work here with cameras, but they do not work. But depends on the sensors, depends on the robots, depends on the technique. Okay. I think that is.
Okay. Any other questions? Okay, no more questions. Thank you very much for your presentation, Professor.
Okay, thank you for the opportunity. I wish I could be over there with you, but that there was a problem I couldn't. But thank you very much for the opportunity.